see here. I want to start off by thanking all the great students that have worked on this project. This has been about a 10-year endeavor that we've been gathering data, getting stuff together. Big thanks to the folks that have funded this work, and a massive, massive thanks to the folks here at the bottom that are my co-authors on this work and worked extremely hard. And I think we should all take a little bit of time to thank Prannoy so much for all of his time putting this together. Everybody, a round of applause, please, for Prannoy. And I'm going to start out talking about just some thoughts on computational tools. I'm going to tap into the person that I think is one of the best acting modelers today. He's very active, he's a great guy. I work with him a lot, and he says this: all computational models are wrong. He says, but they can give us insights that are not possible any other way. And what is he saying there? He's saying that they're not perfect. He's saying that they are useful, they're a place to start, they're powerful, but they're not necessarily perfect. And what do I say? Yeah, look at me. I say computational models that are based on the truth are powerful, but we need experiments to tell us the truth. No, I'm an experimentalist at heart. I do a lot of modeling as well, but I'm an experimentalist at heart, and I work with a lot of people that do modeling. But there are different types of models. You've actually heard all three of them today, and I'll be talking about the bottom two, physics-based and AI machine learning models. But basically, at the heart of this, if you are a young person starting to do this work, make sure you have to ask a specific and reasonable question of your models. Make sure you have lots and lots of useful data for those models, and make sure you check your results and improve again and again and again. And just because your model's not best the first time, you can make it better every single time. Keep getting the data, whatever you have to talk about. I'm going to talk about physics-based models today, and that's where you pick a reasonable model and you adjust parameters. You have adjustable parameters like this, A and B here. You gather data, you tune the parameters, and you check to see if it makes sense. You revise again and again and again and again. Then there's AI-type models. AI-type models are where you might, a lot of folks try to make very, very precise predictions, and then try to look at that, and that's tough because you need millions of observations oftentimes for this, and the results are often not very accurate. But there's another approach, like a clustering approach or a grouping approach, where what if we focused on grouping things into good, medium, or, still better, good, better, and best. You know what I mean? So the high performer, the middle performer, and the low performer. And we've been using traffic lights in civil engineering for a lot of our lives, and they're pretty powerful, right? They're pretty useful. And they only have 3 lights on them. Well, and now they have a bunch of lights, and they blink at you sometimes now, but getting a little bit more complicated in life. But what if we had models that were machine learning based that just looked at the high, the medium, and the low, and what if we could do this only by using the bulk oxides? I'm talking about this. Like you get a fly ash sheet, you look on that fly ash sheet, you get the chemistry off that fly ash sheet, and just use that information. People have been trying to do this for more than 30 years. This is not something that's easy. So if you didn't understand what I was talking about, I'm going to say, like, hey, how does a concrete mixture with fly ash compare to a mixture with only Portland cement? I'm going to break it into 3 different categories. Class 1 would be less than Portland cement by 1 standard deviation. Class 2 would be the same as Portland cement, plus or minus 1 standard deviation. And Class 3 would be better than Portland cement by 1 standard deviation. If you don't understand what I'm saying, it's less than Portland cement, the same as Portland cement, or better than Portland cement. And let's look at some data here. So this is the compressive strength on the y-axis. This is days of hydration here, and you can see all kinds of really, really cool data. But let's focus in here at the end. Let's just pick one data point, and we're going to kind of break this into 3 different categories. Class 3, that's the higher performing. Class 2, about in the middle, and Class 1, the lower. Now we're going to use 30 different traditional fly ashes and 14 different harvested fly ashes. That's 22 Class F, 22 Class C. We're going to test them at 20% replacement and 40% replacement, and we're going to compare the performances with a standard concrete mixture. And what are we going to actually do here? Well, we'll make concrete with a 0.45 water-cement ratio, about 6.6 sacks of binder, 1 coarse, 1 fine, but look at all that stuff we're measuring. Lots of compressive strength, lots of resistivity, lots of diffusion coefficient, lots of heat of hydration. That's 2,655 measurements. That's a lot of data going into this model. A lot of data going into this model. And we're going to compare 5 different machine learning models, and we're going to use all 11 bulk oxides, and we're going to use something called a leave one out cross-validation. So if you don't know what that means, that basically means if I leave out one, I would leave out one data set, I would use the other 43 to train it, I would see how accurate it got, and then do that again 43 times. And that's cool, but then when you go to leave 2 out, it gets a lot larger. You're doing 946 combinations. 3 out, it gets even larger and larger and larger. But we get data that looks like this. So when you start out on the far left here, things are pretty good, about a 94% accuracy in this model. These four other models aren't as accurate. And as you get out here at 80%, or leave P out of 8, that's a large number of numbers being left out there. That's about 80% accurate, and that's all for compressive strength at 20% replacement. And this best model, this one that performed awesome, was something called a kernel principal component analysis. It's in the literature. You can look it up and see what's going on. It's pretty cool. It seems to work with the fabric of this data, is what people say. So you can also look at stuff like this. So let's look at 20% replacement and 40% replacement at different days. And you can see at 3 days there, it's like 98% accurate. And then at 180 days, it drops down to 89% accurate. But on the left there, that is about 94% on average accurate. So that's pretty good. That's pretty solid at getting something, whether it's high, medium, or low. And oftentimes in life, it's kind of what we need to do when we're making decisions, right? Traffic lights have worked with us for a long time, so maybe it'll work for fly ash as well. We can look at things like diffusion coefficient, durability-based measurements. These aren't quite as good, but we go from 83% at early ages, and some would say these longer terms are the much more accurate ones, and 79% accurate. That's an important number because I'm going to show a physics-based model coming up in just a second that's going to do even better than that. And then we can look at heat of hydration. So if you're a mass concrete person, this is a big deal to you. And they are 83% accurate or 77% accurate. See what's going on. And we're making these models better all the time and trying to improve them. So kernel PCA analysis is able to take this bulk oxide content, this problem that we've been working on for more than 40 years, and turn it into something that is somewhat useful to help people make decisions at 20% and 40% replacement using traditional ashes, using reclaimed ashes, and it's about 85% accurate on average. So that's cool. That's a powerful tool. So how could this ever be implemented? What would you ever do with this? Because I'll tell you what, if you have a model that isn't going to help people, think about that. Think about if you can find a way to help people. Well, you basically input these bulk oxides into a simple interface. You have a website that does this, and it's live now. You can log into it with your phones if you want to. tylerley.com/fly ash. And the way it works is pretty easy. You take your bulk oxide content and put them in here. You hit the button at the bottom, and it spits out performance over here. And it even tells you if it's higher, is it medium, is it lower, and it's a traffic light, baby. That's what it's about. And I would say producers, that's what they kind of need. If I'm going from one fly ash to another, what do I expect the change to be? If this material starts to change like this, what do I expect the change to be? And I think that's a very, very useful thing for our industry. So this could be a rapid screening tool to understand how fly ash sources will impact your mixture design. It can investigate blends of fly ash. Yes, we have blended ashes, and this predicts pretty well. We can look at fly ash that does not meet current specifications, and this still works well. And we can build confidence in using and looking and finding harvested fly ash. That's all useful things. So what would we do with this information? This provides much, much greater insights than either Class C or Class F fly ash. And we're about to enter a new era of ash. Get ready. Don't think it's going away. We're going to have tons of ash. Just get ready. It's going to be called harvested ash, though, coming up. So why in the world does this work? Well, at least in the samples that we've looked at for this data set, the particle distribution isn't very that much. And when things get very, very fine, you get different answers. When things get very, very coarse, you get different answers. But in the traditional ones that are out there today that are required by ASTM C618, that's a pretty limited thing. And we've always known that chemical composition is important. We've always said things like Class C is greater than 18% calcium oxide, Class F is less than 18%. Now we just take into account all the oxides. So if maybe you've seen something like this, if you are a concrete freak like me, where you've got something like some kind of silica, calcium, aluminum, and you see where the different SCMs, and this has been useful. This has served us for decades and decades and decades. But ladies and gentlemen, we now have an 11-sided figure that we can look at all these crazy planes in and see what's going on, because that's what this analysis is doing. Okay, it's thinking about things in a dimensional level that we're not used to, right? So now let's talk about physics-based models. So we're going to use a physics-based model to predict the diffusion coefficient. That's one of the same things that I was using before for paste mixtures with 20% and 40% fly ash replacement. And we're going to use a model that was first proposed by Shiheda and Thomas, the great, late Mike Thomas. I miss him. I wish he was here. I miss him. He's gone. But they did this work to predict poor solution alkalinity reduction for ASR type stuff. We said, wow, that's pretty interesting. And we used this, we measured the actual properties of these pastes at a 0.45 water cement ratio, 6 class F, 11 class C, 20 and 40% replacement, and the samples are stored in sealed conditions. We tested them from 45 days, yes, to 3 years. That's a lot of testing, right? And we get data that looks like this. And boy, we could talk about this data for hours, but what's important here is diffusion coefficient is on the y-axis. Days of hydration are on the x-axis, and you can see it goes down and down and down and down. Here's OPC. Class C ash is better than OPC. Class F ash is even better than that. You're like, yeah, I knew that when I walked in. Well, but look at data like this. Wait till the paper comes out. This is going to be an exciting one. We can compare all of these different ashes to one another and see what's going on. But really, all the Fs are pretty similar to one another. See the curves? They're not that different to one another. But look at those Cs. The C's are more all over the place. Some are high, some are low. What am I talking about? I'm going to grab a subset of that. Boy, there's our OPC, there's our Class F, and look at those Class C ashes. One of them is worse than Portland cement. One of them is the same as a Class F, the same. And one of them is in the middle, right? Boy, wouldn't it be cool if there would be some kind of model that would predict this? Well, all Class F ashes are similar. Class C ashes have variable performance, and some Class Cs are just as good as a Class F, but many are not. And some Class Cs are far better than an OPC, and some are not. And again, wouldn't it be cool if we had a model? Wouldn't it be cool? I think it'd be cool. Well, let's start out with this model. And we could talk about where this is from, but I only got a few minutes left. So I can't talk about exactly where this is from, but if you look at the chemistry, if you look at the reactive silica and what it would bind with to produce hydration products, this is what Thomas and his group came up with as a useful parameter, and we started to use it. So we're going to change our A and B to make the best fit, and we get data that looks something like this. Here is that model at the bottom, physics-based model at the bottom on the x-axis. Here is the actual measurements on the y-axis. Here's our friend Portland cement. And there's the model itself. R squared value is about 0.87. And look at that. That's pretty cool. That does pretty well. But there's more useful data in here. Let's go back to our traffic light. Let's look at a simple model. Straight up reactive silica. That's it. One parameter. And that one parameter itself can break us up into a low diffusion coefficient group, a medium diffusion coefficient group, and then a much higher than diffusion coefficient group. And this is the type of recommendations that we can get from models, the insights that we can see once we have this stuff simplified in such a way that makes it really easy to make decisions on what you're going to do. Right? But there are some outliers here. Look at that. What happened? Didn't fit the model. It's not perfect. What's going on there? Variation's not perfect. A little bit larger than we wanted it to be. But that's okay. We keep going. This physics-based model was derived to predict the diffusion coefficient with an R squared value of 0.87. That's pretty good. The simple model based only on reactive silica, SiO2, was able to predict low, medium, and high performance really, really simply. And there's one outlier, and there's some variation. So in general, how can this be used? Well, this amount of SiO2 is something you probably may not forget if you're a fly ash person. And you're going to try to use this in your life. Okay, that's powerful. And if you add calcium oxide in the alkalis, you can get better qualitative predictions. And so, ladies and gentlemen, I just showed you that a physical-based model outperformed a machine learning model. Okay? And I think that's a cool observation and something to think about. AI machine learning is great, but it needs lots and lots and lots of data. It needs to be pointed in the right direction. If you send it off on a wild goose chase, and that's kind of what the first presenter was talking about. Physics-based models are powerful, though, but they are restricted to the model that you use, what you think in your mind, or what we think is real. And an observation is when you blend this physics and AI machine learning models together, they can compensate for each other. Okay? And as you restrain the AI machine learning model, you need less data. You showed us great data of that. And there are lots of ways that we think we understand the world that AI and machine learning are going to tell us are totally wrong, that we need to revisit ourselves. So an important statement, you're only as good as your data, spoken by an experimentalist, and you must validate your models and be careful not to overstate their usefulness. And baby, it is all about constant and never-ending improvement. That's what you say. This is about 15 years worth of work. Okay? Takes a while to finally hit pay dirt. In conclusion, computational tools are powerful and will help us develop new understanding and insights into long-standing questions. This kernel PCA model can predict the performance of both traditional and harvested fly ash for strength, resistivity, diffusion coefficient, and heat of hydration. The other ones didn't do as well, but this one did because of the way the data is organized. And the physics-based models were useful and provided accurate predictions and even less computation. And you should use whatever model is best for you, with the data you have and based on what you want to learn. So I have to take this moment to plug my YouTube channel. I am at 98,000 subscribers, and I bet, please, there's got to be somebody in here that can jump in, like, subscribe, leave a comment below, right? And then that is the video that or that is the website that I plugged. And if you have any questions, let's bring it, ladies and gentlemen. Let's go concrete. Thank you.